Good morning, aspirant. In this video, your every doubt about SN1, SN2, SN dash, SNI, E1, E2, E1CB, EI are going to get cleared. So, let's discuss reaction mechanism on sp3 center. We know there are many kind of reaction. For example, a nucleophile can attack two sp3 carbon. It can attack sp2 carbon that we study in carbonyl chemistry, right? Because in carbonyl, this is a carbonyl compound, and as the oxygen is delta negative, then this carbon will be delta positive. The nucleophile will attack on this carbon. So this carbon is basically sp2. So here the reaction occurs on sp2 center, but majority of reaction occur on sp3 center, and we are going to discuss that. So we are going to study reaction mechanism on sp3 center, not always sp3 carbon, but sp3 center. Now in this reaction mechanism, first we are going to classify it. There are two major segments. First one is substitution. I request everyone to play this video at 1.5x, and if the ink is not clearly visible, then increase your resolution to the maximum 1080p or 720p. Okay, so first type of reaction is substitution, second type is elimination. So we are going to take a broad look on this kind of reaction. In detail, we are going to discuss later each and every segment. Okay, so this video is of broad understanding about the processes. Okay, so for substitution reaction, there are few type of substitution reaction. These are SN1, substitution nucleophilic 1, substitution nucleophilic 2, substitution nucleophilic 2, sorry, SN1, SN2, SN dash, SNGP. NGP means neighboring group participation. Okay. Then SNI. If I talk about the importance of these five reactions, SN1, SN2 are most important, then SNGP. Okay. So these reactions are more frequent. Okay. If I take 100 substitution reactions, then majorly we will found these three reactions. Okay. Now, if I classify elimination, I will get four type: E1, E2, E1CB, CB means conjugate base, and EI, I for internal. Now, before understanding these things, the entire classification and their differences, I'm going to tell you few things about solvent. Okay, because the reactions, organic reactions, mostly occur in liquid medium. Why? In gaseous medium, particles are far enough. In solid medium, particles are too rigid to move. So liquid phase is the best medium for organic reaction. And reaction occurs in some solvent. So if I classify solvent, then majorly two type of solvents are there. One is polar protic, PROTIC, polar protic. Then, sorry. First part of classification will be polar, second will be non-polar. Polar means dipole moment not equal to 0. Non-polar means there is no pole, that means dipole moment 0. For example, benzene, toluene, carbon tetrachloride, this kind of solvents. Octane, hexane, okay? Polar further classified into two parts: polar protic, polar aprotic. Polar protic means those solvent where we get hydrogen bond. For example, water, for example, alcohol. But polar aprotic means here no hydrogen bond is there. For example, DMF, dimethyl formamide, DMSO, dimethyl sulfoxide, are this kind of example. Okay. Polar protic solvent is preferred by SN1 reaction. If we put polar protic solvent in SN1 reaction, so it will favor SN1 process. Polar aprotic will favor SN2 process. Okay. Now, let's discuss one by one SN1, SN2, and this sort of things. Okay. So first SN1, what happens? For example, I have one substrate that is this. Okay. C, CH3, 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 Cl. Now, this will undergo reaction and with OH minus it is going to react and my final product is this OH. So here what happens ultimately? Cl is getting replaced by OH, and in another word I can say OH is going to substitute Cl. That's why the reaction is substitution reaction. Here substitution can occurs in many ways. Suppose in the first manner what can happen? First this thing can happen. For example, first step, Cl minus will get removed. So this Cl will be removed as Cl minus. That means carbon chlorine bond pair is going to shift on chlorine. So we will get one carbocation, right? Basically this angle will be 120 degree, right? Because carbocation is sp2. So this is basically sp2 carbon and this is basically carbocation. Is this stable? It should be stable. Otherwise this will not form. It should be stable. And it is here at this particular structure, it is stabilized by 9 hyperconjugative structure of 3-methyl group. In the next step, what can happen? This OH minus is going to attack here and this final product will form. Now, the thing is, here two cases can occur. Let's see. I know my carbocation is sp2 carbon. That means it is planar. For example, if I take 3 groups, suppose R1, R2, R3, these are 3 groups. So here we will find R1, R2, R3. Okay. Now, what happens if I draw a 3D structure? For example, this is the carbocationic carbon. Here I have R2. Here I have R1. And in the above the plane, I have R3. So this is basically sp2. So one pz orbital is there, isn't it? So this carbon is basically positive. Now what happens? If my OH is going to approach this carbon, then it has two ways. It can approach like this or it can approach like this, isn't it? So if from topward it approaches, then the final product will be, see, it will be like this. OH, R2, R3, R1. If it approach bottomward, it will be R2, OH, R3, R2, R1, right? So these two product is going to form. And as you know, both the faces of the carbocation are of equal steric hindrance. So both things are going to generate in the same amount. And if you closely notice that these two are mirror image to each other and non-superimposable, so that are enantiomer. We know the equimolar mixture of two enantiomer is called racemic mixture. So basically, we are expecting that a racemic mixture will form. Because if I have 100 OH molecule, then 50 will approach from top and 50 will approach from bottom. So this product will generate 50 molecules, and these are also 50 molecules. So equal amount of two enantiomers. This is basically a racemic mixture, but practically racemic mixture doesn't form. Why? Because one of these is partially a greater amount. Why? Because when the OH is basically, when the chlorine is leaving and OH is approaching, at that particular point, OH minus cannot approach from backside because there is more steric hindrance. So in the initial here, first transition state, in the first transition state, it get a little favorability, or it get a little advantage from approaching topward side. Okay, so one of them will get a slightly major amount, but mostly racemization will occur. Mostly, for example, I will be getting 49 this molecule and 51 this molecule, like this. One of this is going to be major, but in a very little extent. Now I have used one term, transition state. What is this? Transition state is not a particular compound or an intermediate. Here in this total process, it is a two-step process. So in SN1 reaction, two step is involved. Okay. And one intermediate is formed. This is carbocation intermediate. And in carbocation, we know it is 2 carbon, 2 carbon, 2 carbon. That means 6 carbon, 6 electron species. 6 electron means it is electron deficient. It is electron deficient, so it will be stabilized by electron donating groups. So more the electron donating group I will be getting here, more stable the carbocation is, right? Now, from species 1 to species 2, for example, it is species 1 and this intermediate is species 2. The midway is basically a transition state is when the Cl bond is 50% broken. Half of the Cl bond, carbon chlorine bond is broken. This is basically transition state. So transition state 1, here first transition state will look like R1, R2, R3, Cl. So this will be our first transition state, and it is written like this in third bracket and this sign. Okay, this indicates it is highly energized. This is very much unstable. Okay, and from here also, we will be getting transition state 2, and the transition state 2 will be looking like R1, sorry, like this, R1. If for this molecule transition state I am drawing R1, R2, R3, OH. So this will be our transition state, second transition state. Okay. Now let's see the energy profile diagram and a rate expression for this reaction. I am wiping this up. Now, as I have told you that polar protic solvent will favor this transition state or favor SN1 reaction. Why? Let's first discuss the energy profile diagram for SN1 reaction. Energy profile diagram for SN1 reaction, you can make an heading. Energy profile diagram. Here three species is there. First reactant, second intermediate, third product. We know that reactant and product are neutral molecule, but the intermediate is positively charged. That means it is unstable. It is less stable than the reactant or product. So if my reactant energy is this, or if my product energy is this, then obviously the intermediate carbocation will have more energy. That means less stable. Okay. And I have drawn the product here. I could have drawn this here also. What makes the difference? I am telling you after 1 minute. Now, it is reactant. It is my product. So basically here it is my reactant. This is my product or products. Okay. So from reactant, first we will draw like this. Okay. And second, we will be drawing like this. Okay. So this is our energy profile diagram. It is our intermediate or carbocation. Okay. This is our basically, it is high energetic. I have told you that this sign, this hash sign is for a sign or double dagger sign. This is for high energy. So it is transition state 1. It is basically transition state 2. If I have drawn the product like this, that means from reactant to product, I have this extra amount of energy. So this is basically exothermic reaction. Okay. If I would have been drawn the product like this, then my reaction would be called endothermic reaction, where the product energy is higher. That's the difference. Okay. So this is the energy profile diagram for SN1 reaction. Now, in these two steps, which step is a rate determinating step? That means on which step the reaction kinetics depends. That means on which step it depends that how much product will form. It is the first step. Why? Suppose my reactant to carbocation to product, which step is faster? If I say reactant to carbocation, that means a neutral molecule to a charged species. It will not be favored, right? Nobody will uh, want to generate a charge on it. So this step is slow. But one charged species is very much unstable. So it will try to stabilize into product, a neutral molecule, very fast. So this is basically fast. So this is a slow step, and the slowest step is basically called a rate determinating step. So in this SN1 process, step 1 or carbocation formation step is the rate determinating step. And that's why the rate of reaction is equal to rate constant into concentration of reactant only. That means the rate of reaction doesn't depend on that nucleophile, that is OH minus. In the second step, OH minus is involved, right? But the rate doesn't depend on OH minus. The rate is dependent on reactant concentration. So this is basically rate equation. And as in the reactant concentration, power is 1. Okay, here only one species in the rate equation and its power is 1. That's why it is first order reaction. And in this reaction, we'll be calling it molecular molecularity equal to 1. In this reaction, molecularity is 1 because in the RDS, in the redeterminating step, only one species is involved. That's why molecularity is 1 and it is first order reaction. And where molecularity is 1, this reaction is called, as molecularity is 1, this reaction is called unimolecular reaction. So it is unimolecular reaction. If molecularity is 2, then we would be calling it as bimolecular reaction. It is here, it is not. It is here unimolecular reaction. So SN1 reaction is unimolecular reaction. The things you are learning here may be asked you in so many formats, so many informations are there. Okay, so try to consolidate things. Okay, so this is basically unimolecular reaction. That's why when we study SN1 reaction, it is basically called nucleophilic substitution unimolecular, 1 for unimolecular. Why this is called, we call it substitution. It is understandable because OH is substituting itself with Cl. This is substitution. Why nucleophilic? Because a nucleophile, OH minus is nucleophile, right? With negative charge. So it is basically replacing someone. So substitution by nucleophile. That's why it is a nucleophilic substitution, and 1 for unimolecular. If someone asks you that in SN1 reaction, why this 1 stands for? Is it for number of steps? Is it for number of intermediate? Here, number of intermediate is also 1. But this one is not due to number of intermediates. This is basically due to molecularity equal to 1. It is first order reaction, right? I hope you got the clarity. Okay. Now, one thing I want to make you understand, if I change the starting material a little bit for your better understanding, I am changing this starting material a little bit. If you are making notes, then try to make a separate diagram for this. Okay. Suppose I am keeping this in mind. Suppose I have my Cl here, R2 here, R3 here, and R1 here. So this was, suppose this was my starting material. Suppose if I make RS nomenclature at this center, this is basically R. I am changing a little bit. Suppose I had OH here, and OH is basically star marked because it is radioactive leveled. Okay, this is O17 or O18. If you make RS nomenclature on this center, and if you find it R, then in the product, in this product, you will be getting what? R or S? It is also R. But in this, you will be getting S. If the configuration is same, then I will be calling it here retention of configuration has occurred. Retention of configuration. And here I will be calling it as inversion of configuration. Okay, inversion of configuration. So two system will form here, and I have told you that when OH will be removing here, first step OH will get removed, so oil will be removed here, so one phase will get preferred. That's why one of these two will generate a little bit more. Okay, that's fine. So this is our SN1 reaction. On which factors this SN1 reaction depends? Let's take a look. On which factor this SN1 reaction depends? I have told you that rate is dependent on uh, our reactant concentration to the power 1, and first step is rate determining step. So more the first step in the rate, overall rate depends on the speed of that first step. So more speedy the first step is, more will be the rate of reaction. And on which factors it will depend? First factor, stability of carbocation stability. If more stable the carbocation, then basically this first step will be faster. Okay, not faster than this, but comparatively faster. So more the carbocation stability, more the rate. Okay, second, electron donating group on carbocation. It is also basically the extension of first point, because more the electron donating group, the more will be stabilized the carbocation is. Okay, so this is basically obviously increasing carbocation stability. Third point, third point is third point is transition state down. If the transition state is lower, then the process will go faster. Okay, and how this will be going? This will be preferred by polar protic solvent. What will happen? Polar protic solvent will stabilize this carbocation with hydrogen bond. So that will basically decrease the energy of transition state, and that will favor the reaction. Okay, so I hope it's clear now. So this is basically substitution nucleophilic unimolecular. Okay, now, so if I compare 1 degree center versus 2 degree center versus 3 degree center, then 1 degree to 2 degree to 3 degree, we know this is basically I have drawn 3 degree. That means more hyperconjugation. So more hyperconjugation means more will be the rate. So 1 degree to 2 degree to 3 degree, generally rate increases. Okay. Okay. So now we are done with first process, our SN1 process. And now let's discuss SN2. SN2. I have told you initially that our ultimate goal is to convert one compound, and we were going to replace it with one nucleophile. Suppose my initial compound is like this: OH star R1 R2 R3. Now what happens here? This carbon oxygen bond, we call it sigma bond, right? In its opposite, here sigma star bond is present. Sigma star means anti-bonding. What happens if my nucleophile is OH? It can be anything. So OH minus will attack on the sigma star, and then this carbon oxygen bond will break, and OH star minus will be removed. So what happens? I am drawing now transition state. Okay. In the transition state, we will be getting R1, R2, R3. Now this OH is just approached, and this O star H is getting removed, but it is 50%, it is 50%. Okay, 50% bond formation. This bond is formation, this bond is breaking 50%. This is basically our transition state. This is not intermediate. So practically we cannot isolate this compound. Okay. So, okay. So finally we are getting what? Let's see. Finally we are getting OH, R3, R1, R2, like this. So this will be our final product. Here what happens, if this is R configuration, this will be S configuration. So here inversion of configuration occurs. Inversion of configuration of occurs. Why? Why this occurs? Because here we see backside attack. Backside attack. Right? So backside attack occurs in SN2 reaction. That's why we get inversion of configuration here. Now, as there is backside attack, and if the groups are large, then the backside attack will not be preferred. Right? That means if groups are bulky, bulky means larger, then rate will be slow. Okay. This reaction is basically a single step reaction. This is basically transition state, isn't it? So practically this doesn't exist. This exists, but practically we cannot isolate it. So this is basically one step reaction. Okay. So from this to this, these things formed because this is basically a continuous step. This bond is breaking and this bond is forming. So this is basically going on, and finally we are getting this product. Okay. So this is basically a single step reaction. As in the last reaction, it was a double step reaction, two step reaction. In every step, there will be a transition state. So as here one step, so here we get one transition state. So this is basically, if I write here, steps equal to 1. Okay. If it is step 1, then the only step is this. So this step is basically rate determinating step. So a rate equal to rate constant into, here you can see two things are involved. Initially in the RD step only one species was involved, but here two species are involved. What is that? Reactant and nucleophile, isn't it? This is basically reactant and this is our nucleophile. So here in this side, total power is 1 and 1, 2. So order of reaction is 2 and molecularity is 2, because in RD step 2 species is involved. So molecularity is 2. That's why this is called nucleophilic substitution bimolecular. Molecularity is 2 means this is called bimolecular. Now let's see what is the energy profile diagram for it. Suppose I have this reactant and I have this product. I am making for exothermic reaction. That's why I have written the product is a little bit lower. So, and it has only one transition state. So this is basically our energy profile diagram. Right. Now the thing is, there are two things on which the rate depends. Isn't it? There are two things. So there will be more factors which will determine the rate of the reaction. One thing I've told you, that the solvent thing. One thing I want to emphasize, that if I want to mention that how this transition state looks like, you will be agreeing with me that this is basically a TBP geometry, trigonal bipyramidal. So transition state is TBP. And in TBP geometry, generally in TBP geometry, if I draw one central atom, then I draw one TBP geometry, then there is basically 10 electrons are involved. So this is basically electron rich system. That means electron withdrawing group will stabilize it. As it is electron rich, then electron withdrawing group, if it is electron rich, then more the electron withdrawing group that will withdraw electron from here, that will stabilize this system. So electron withdrawing group will stabilize transition state and rate will increase. But in the previous case, if there was electron donating group, then that was stabilizing the carbocation and that's why it was increasing. But here it's the opposite. Now, on which factors this thing depend? The rate depends, because in exam he will get questions that compare the rate of SN2 or compare the rate of SN1. Sometimes SN2 reaction is called acetolysis reaction. Acetolysis. So in question it will be written that compare rate of acetolysis. Then you have to understand that it is basically SN2 reaction. Similarly, for SN1 it is often called solvolysis. So in question if mentions the compare the rate of solvolysis reaction, then you have to compare the rate of SN1 reaction. Now, on which factors rate depends? As we know, transition state is TBP, then electron withdrawing group will stabilize. That means R1, R2, R3, if there are more electron withdrawing groups, then rate will be faster. Okay, now rate depends on few things. First one is substrate, or I can say reactant, then nucleophile, then solvent, then orientation. As it attacks from backside only, that means this molecule should have some particular orientation to allow that OH to attack from backward side. Okay, then substrate or in reactant, we know if steric hindrance is less, then the rate will be higher. Why? Because this is if there are large groups, that means bulky groups, then rate will be slower. Will not able to approach. OH will not able to approach, and nucleophile will not able to approach. So if steric hindrance is low, that means small groups, then rate will be higher. That's why 1 degree to 2 degree to 3 degree, this is the rate order. 1 degree means, for example, CH3OH. For example, in the system, if I would give CH3OH, a 2 degree alcohol and a 3 degree alcohol. So another OH star, or for example, I am taking another nucleophile, for example, Cl minus. So this will approach here, this will approach here, this will approach here. Here it will get more steric hindrance, so it will not able to approach here. So rate is faster in the first case. Okay. So first one is steric hindrance. Second one is electron withdrawing group. This is basically if more electron withdrawing group, then rate will be higher, because more electron withdrawing group will stabilize the TBP transition state, which was electron rich. That will basically drop this transition state. Okay, stabilize the transition state. So rate will be faster. Second, nucleophile. Strong nucleophile will have more rate than weak nucleophile. Okay. If we go from top to bottom in a periodic table, for example, F minus, Cl minus, Br minus, I minus, then nucleophilicity increases. Nucleophilicity increases from top to bottom. So I minus is most nucleophilic. Okay. And from left to right, if I say, so for example, oxygen, carbon, oxygen, nitrogen, F minus. So F minus is more electronegative, so it will not uh, donate its electron to any electrophile easily. So this is basically more nucleophilic. Okay. So I can say here rate proportional to 1 by chi. That means electronegativity at period. In any period. These are in a same period, oxygen, nitrogen, fluorine. Then chi of fluorine is higher, then the rate will be slower. Right? Okay. Also, a rate will be inversely proportional to steric hindrance. For nucleophile also, for example, I am taking a small nucleophile for, and in contrary I am taking a very big nucleophile, so it will not able to attack here easily. So smaller nucleophile is preferred and a smaller steric hindrance is preferred. Right. Next, solvent, as we know, polar aprotic solvent is more favored than polar protic solvent than non-polar solvent. Okay, but in the SN1, what was the case? The opposite was the case, right? Polar protic was the fastest rate, then polar aprotic, then non-polar. Now orientation. Orientation is a great fact. For example, suppose I have this particular molecule. Okay. Here, what happens? For example, I have this Cl and this is our H. And if OH minus nucleophile attacks from backside, then it will approach from here, from backside only. So what happens? Final product will be H will be upper. So OH has approached from lower side, then hydrogen will be at upper side. Okay, so this is our final product. This product is basically exo product. That means it is moved outside the structure. So this is exo product. But our product is endo product. Okay, this is inside. Okay, inside this, in this zone, if the group is, that is endo product. Okay, if it is in outer side, then it is exo product. So we are getting here endo product. So that means geometry matters. All right. uh One more thing, this substrate doesn't show SN1 reaction or SN2 reaction. For example, this bromine, this kind of system, if the leaving group, this group is called leaving group, this OH is leaving, so this is basically leaving group. Okay, if this leaving group here, Cl is the leaving group because this is leaving and this is joining, so this is leaving group. So leaving group, if it is in bridgehead position, if it wish to go to the product by SN1, what will happen? First, carbon bromine bond will break, then carbocation will form. So it will form a bridgehead carbocation. That is very much unstable. So this will not form. So SN1 will not form. But SN2, if for SN2, what happens? Backside attack happens. Suppose my nucleophile is OH minus. OH minus have to approach from here, but in the front ring, this bridge ring in the front side. So this will not allow OH to approach. So in this substrate, neither SN1 nor SN2 is observed. Okay. So we have dealt with SN1 and SN2. Okay. Let me see. I am left with any information or not? No. Now the most difficult part, SN2 dash. SN2 dash. See, if a substrate is like Br and OH minus is there. If OH minus is there, what will happen? In first case, it has two options. Okay, in this type of substrate, generally SN2 dash reaction occurs when nucleophile has two options to attack. We generally know it shows backside attack, so this will attack here and Br minus will be leaving. So this is basically SN2, right? It has another option. Okay, another option is it can attack here. Okay, then carbon, this pi bond will shift here, then carbon bromine bond will left. I am showing you with a different color for your better understanding. Okay, so second option is this. Okay, here also it has two options. One is this, another one is this, and a normal SN2, like here it will attack, and this. In which case, which path will be favored? In the red path, I am showing SN2, and the green path, it is basically SN2 dash. For first case, if I know this center is 1 degree center because only one carbon is attached with this, but this center is 3 degree center. So here more steric hindrance of 2 methyl group. So this increased steric hindrance will not allow this path. And for the first case, if this one to approach here, here is 2 methyl group also, here is also steric hindrance. So this in the first case, this path will not be allowed. So in first case, red path will be allowed. That means basically here SN2 will occur. But in the second case, we will have SN2 dash. For SN2 case, what will be the product? Basically simply we'll be replacing it with OH. But here, what will be the product? Like this, isn't it? So OH will be connected to here, and here methyl. I have drawn this methyl. Okay, then carbon carbon, I have written carbon carbon, then a double bond will be there because this bond is shifting here and this bromine is removed, so we are left with 2 methyl. This is a 2 methyl. So these is my product, final product of SN2 dash reaction. Okay, one more thing, one more confusion. Then what will happen compounds like this? Mm, like this. Then if I have OH, then where I will make it attack. Here one methyl group is there, so steric hindrance is there. So this will attack here. Okay. So normal SN2 will be there. Okay. I think it's clear to you. Okay. So this is basically SN2 dash reaction. So SN2 dash is basically SN2 at conjugate position. Conjugate position. Conjugate position means, for example, I have one this double bond O. For example, OH minus is going to, not OH minus, for example, a nucleophile, for example, NU, nucleophile minus. So it can attack here, or it can, sorry, this oxygen is delta negative, this is delta positive, and as this is delta positive, then if it undergo resonance, then then this portion will also be positive. So two positive center is there. One is direct, one is conjugate. So this is direct attack, this is conjugate attack. So here SN2 dash is basically SN2 with conjugate attack or conjugate position. Okay, I think now it's clear. Okay, now the next reaction is our SNGP SNI. Okay, my slide has ended, so I have to add one more slide here. Okay. Okay, now our topic is SNGP. NGP means neighboring group participation. So your neighbor participates. Okay, but it's not neighbor like our society who doesn't support our growth practically. Okay, so these neighbors are very much supportive. Okay, actually supportive. So what happens here? Neighbor groups will support a reaction. Suppose this neighboring group will support a reaction in three ways. Okay, it can support by using lone pair, by using aromatic ring like benzene ring, and by sigma bond or by pi bond. So in these ways, these neighbors can support. Okay, let's see how this thing occurs. For example, I'm taking one compound here. This is basically an example from, this example is given in NCERT itself. Suppose Cl here, and I'm treating it with OH minus. What happens? First carbocation will form. So this is basically approaching to SN1, right? Now what happens? This system, if you don't know this SNGP concept, then what you will do? You will make a hydride shift here. So you will make one stable carbocation like this, and then you will treat OH minus, that will attack here. So you will be making product like this, but this is not the final product. Okay, what happens here? This carbon carbon pi bond, carbon carbon pi bond will stabilize this. How? Suppose this pi bond, this carbon has taken and uh, sorry, this carbon, this pi bond has shifted here. So pi bond has shifted here and the positive charges came here. Okay, so this is our basically neighboring group participation. So this is basically neighboring group and this Ngp is showing by aromatic ring. So aromatic ring is basically stabilizing that carbocation. Now what happens? We can write it as resonance hybrid of like this plus. Okay, because resonance will be occurring here. Now our nucleophile OH minus can attack in both ways. It can attack from here or it can attack from here, but from where it will attack? To do so, we have to perform a test. What test? Here, these two bond, any of these two bond will break. Okay, any of these two bond will break like this. Okay, and the aromaticity will be set up. If this bond breaks, then carbocation will be here. But if this bond breaks, carbocation will be from here. This carbocation is more stable because it's, if it breaks, then it is 2-degree carbocation. But if it breaks, it only if this bond breaks, there is a 1-degree carbocation, right? So this carbocation, this bond if breaks, then more stable carbocation is formed. So this bond will break. So basically this carbocation will be attacked by this OH minus. So this path will follow. Then our final product will be, so this bond will break. This will again set up the aromaticity. And our OH will be here. So this will be our final product. This is basically Sngp with aromatic ring. This Sngp occurs in so many ways. For example, if for a pi bond, I'm showing you. For example, this is our substrate. This is the leaving group. Okay. One is this versus one is this. Like this. Another one is like this. This is leaving group. This is leaving group. If they say to compare the rate of SN2 or SN1, whatever they say, substitution reactions, then what will happen? This pi bond will show very much, you know, neighboring group participation. So what will happen? This bond, first leaving group will leave, then the carbocation formed will be stabilized by this pi bond very easily. But this pi bond will not be that much efficient to do that neighboring group participation because geometry is not allowing. So it is not in the backside. So here is very high Ngp, so rate is higher. So it is less Ngp, so rate is lower. And here no Ngp, so no pi bond, no Ngp, right? No pi bond, no Ngp. Sigma bond Ngp is very, very rare. Very, very rare. Okay. So this is basically our neighboring group participation. Okay. In many cases, these things happen. For example, this is chlorine. Then suppose mm, for example, I have one lone pair containing species here. So if it gets removed, then this will stabilize here. Okay. This will stabilize here like Ngp. X, A, like this. Again, what happens? Among these two bond, which bond will break to make more stable carbocation? This bond will break because this will lead to more stable carbocation here. So our nucleophile will attack now here. So our final product will be here. We will get nucleophile. So this will be our final product. So in these cases, neighboring group participation occurs. For more details, we will study later some special examples and more practice question we will solve later. Now Sngp, and now it's last of substitution reaction, that is SNI. What happens? For example, my compound is like this, ethyl alcohol. I am giving it SOCl2. I am making a treatment with SOCl2. Then what happens? Suppose I have this alcohol. Okay, this alcohol. What will happen? OSOCl will form. like this, S double bond O, Cl, Cl, SOCl2, and this is our alcohol. Okay, so OH minus will attack here, then this will break. Then what happens? Cl, S, Cl, O minus, O, like this, and O minus gives, and this is removed. So SOCl, OSOCl will form. Okay. Now what happens? I have left with one Cl minus, this Cl minus I have left with. Okay. So this Cl minus will attack here. Now what happens? This Cl. So this reaction is basically SN2, isn't it? So this is basically SN2. So here inversion of configuration will occur. In SN2, inversion of configuration occurs. We know if it is R, then it will be S, right? As in this case, this center is not chiral, no RS concept will be applied here. But if it is a chiral center, then R will be S. But this is also sometimes not true. Sometimes R will not convert to S. This will be inversion. Inversion of configuration does not mean that configuration will convert from R to S. It can convert to R to R also, because we don't know that what is the priority of the upcoming group. If the highest priority group is removing and the highest priority group is approaching, then it will be R to S or S to R. But if the priority is getting changed, then we have to see that what is the configuration. But inversion means from opposite side. Okay, leaving group and the upcoming nucleophile are from opposite side. If it is so, then it will be inversion of configuration. Okay, this is basically SN2, but this is not SNI. For example, I have this OH. Then what happens? I have one solvent like this. Okay, what happens when solvent first attacks? If solvent is nucleophilic, then this will attack first. Then what will happen? O, this solvent is attached here. Now what will happen? So in the first step, it is basically one SN2 process. So here it will be inversion of configuration. Now what will happen? That OH minus we are left with, or if we now treat with SOCl2, then with this process, ultimately what will happen? Finally, for SOCl2, first we will be forming OSOCl, then again we will be getting this Cl. Now from this to SOCl2, this is basically another SN2, then this is again inversion of configuration. If two inversion of configuration is occurring on the same center, first inverting, then again inverting, then it will be basically the starting configuration is retained. So here ultimately the overall, if we see, then it is basically retention of configuration, and this is basically SNI reaction. SNI reaction means double SN2. It is basically double SN2. First SN2 is by solvent when the solvent is nucleophilic, and second is the natural SN2. I can give it here Cl minus also, so it will also replace. So second step is simple SN2. So first step is SN2 with solvent, second step is simple SN2, and as 2 SN2 is involved, then ultimately we are getting retention of configuration. So that's why it is called SNI reaction. I means internal and retention. So important point here is retention of configuration and internal reaction. Internal, that means the nucleophile is solvent itself. So in the reaction itself, in the solvent itself, it is participating in the reaction. So that's why it is internal. So it's an I for internal. Okay. So I think all SN reactions now it's clear to you. Now the final step, we're going to learn all elimination reactions. Elimination reactions. First, it is E1. Second one, it is E2. In this page itself, we will cover it. Third one is E1CB. Fourth one is EI. In E1, what happens? In elimination, what does elimination means? First, look at this. Suppose I have one leaving group here. The carbon attached to the leaving group is alpha carbon. This is beta carbon. If I have one beta hydrogen attached with beta carbon is beta hydrogen. If I have one beta hydrogen and I have one nucleophile, then I get final product like this. Nucleophile bond hydrogen, leaving group is removed, and this alkene is finally removed, CH2 CH2. So these are our product. So in these following ways this can form. Let's see first how it will occur. Suppose I have one leaving group here. For example, I'm giving bromine as leaving group. Okay, here I have hydrogen and methyl. Okay, I have methyl. First I'm taking hydrogen. Okay, now what will happen? First step, what will happen? SN1 like E1. SN1 is like E1 type of reaction. What will happen? Hydrogen, hydrogen, hydrogen. Carbon, positive carbocation will form. In the second step, what will happen? I have one nucleophile. For example, nucleophile is OH minus. Generally, base is used, so OH minus generally used. So this will happen. So I know here I have two hydrogen. I have also here two hydrogen. So hydrogen, 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 hydrogen. C double bond C. And here Br minus is removed. So plus Br minus plus OH nucleophile with hydrogen will form H2O. So this is our final product. So in elimination, always alkene will form. Okay, alkene will form. Okay, so this is basically SN1, right? Carbocation is formed. So all the factors responsible to stabilization of carbocation will facilitate the reaction. So rate will be higher if the process is faster. And this is basically E1Y. One is again for unimolecular reaction like SN1 reaction. Okay. Now second, E2 reaction. E2 is like obviously SN2. What will happen? For the same reaction, bromine, hydrogen, 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 hydrogen. What will happen? I have OH minus. The single step. This. So this will attack here. This bond will break to this, and this will remove. So final product is all obviously same. Final product will be this only. So this is a single step reaction, and in the single step, two species are involved. So this is basically E2. Two means bimolecular reaction. Now there is a glitch. What is that? Two type of products can be formed here. Two type of product are Hoffman and Sngp. So we're going to learn Hoffman product versus Sngp product. Sngp product. Normally, Hoffman product will be minor product. Minor product means it will form in least amount. Sngp product will be major product. But if the living group is NR3 plus SR2, R means any alkyl group, or if these are living groups, as here I have written bromine as living group. So if these are living group, then Hoffman product will be major, Sngp product will be minor. How we will understand that which product is Hoffman, which product is Sngp? Sngp product is where more hyperconjugation is there, that is Sngp product. Hoffman product is less hyperconjugation. This is basically Sngp product. Let's understand with one example. Suppose I have this bromine as living group and this. Okay, this is our substrate. Then this is alpha carbon, this is beta carbon, and this is also beta carbon from this side. So if I have this beta hydrogen, this is also beta hydrogen, and this is also beta hydrogen. So if OH minus perform SN2 here from this side, this, my product will be this. But if my OH minus approaches like this, so my product will be this, and obviously with this trans product, cis product will form. Okay, so one type of product is this, another type of product is this. Okay, these are my two products. Okay, Now this, in this structure only 2 alpha hydrogen is there, and here 336 alpha hydrogen is there. So that means it is Sngp product and this is Hoffman product. Okay. And now which one will measure? This is the normal case because living group is not like this. Okay. If these three are living group, then it is a special case. But it is normal case because living group is not like this. Okay. So normally we know Sngp product will be measured. So this product, sorry, Sngp product means more hyperconjugation. So this is Sngp, this is Hoffman. So at normal case, Sngp will be measured. So this will be measured. If I identify it, it is product A, it is product B, it is C, then A will be least stable. So if I get 100 molecules of products, then A will be least. Okay. And B and C will be measured. And among B and C, we know B will be measured because it is least steric hindrance as is trans product. So B greater than C greater than A, and A will be very least. So this is basically our product composition. In exam, they may ask that what will be the major product or what will be the minor product, like this. Okay. But if my leaving group, in the next example, I can write if I leaving group this change it with F or Nr2 or Sr2, like the Nr3 plus or Sr2, then what will happen? Then also this 3 will be formed. Then also this is Hoffman, this is Sngp. But then Hoffman will be measured. In that case, A will be measured and B and C will be like this. Okay. So this will be for special case. So this is basically Hoffman and Sngp case. I hope you have understood it. Now, third case, our third type of reaction, E1CB. This is very simple. If suppose I have my leaving group here and my beta hydrogen is here, okay, H beta. If I have any electron withdrawing group here, then what will happen? Then if my OH minus, that is nucleophile or base, it will attack here, then this doesn't occur first. First what will happen? This carbon hydrogen bond will shift like this. So carbo anion will form. Okay, here I have leaving group, here I have electron withdrawing group, that's carbon anion will form. Why carbon anion will form? Because I have electron withdrawing group, so it will stabilize that carbon anion. For example, I have electron withdrawing group like this. If I have electron withdrawing group like C double bond OCH3, then what will happen? So this C double bond OCH3 basically stabilize this negative charge, isn't it? So that's why where I have electron withdrawing group, then only that carbon anion will form. So this carbon anion will called conjugate base, because if in any acid HA this H plus is getting removed, then A minus is left, we call it conjugate base. Here also this acidic hydrogen is removed, so this is basically conjugate base. That's why it is called E1CB conjugate base. In the second step, what will happen? This will happen. Okay, electron withdrawing group. So this is basically our E1CB. More the electron withdrawing group, faster will be the process. Okay. Now last, EI. I am taking another slide for this. Okay. I have to take one more slide for that. Okay, fine. EI. This is very interesting. EI. I for internal. What will happen? Suppose in this system, I have living group here. But here the living group is kind of different. For example, I have one atom Y and one atom X is here. X and Y are heteroatom. Heteroatom means atoms apart from carbon and hydrogen. All atoms are heteroatom and they have lone pair. Okay. Suppose X and Y have lone pair. What happens? With this compound react and final product is C double bond C plus XY. This is our final product. So this is basically EI reaction. And these two these two groups must be syn periplanar. Syn periplanar. But for SN, for E2, the groups should be anti-periplanar. For example, this living group, this hydrogen, suppose this hydrogen, hydrogen, this was the substrate we have taken for SN, we had taken for E2 reaction. These two groups should be anti-periplanar for E2 reaction. I forgot to write. These two, let's see, these are anti-periplanar, like this one, like this. This is anti-periplanar, okay? One is up, then another is down, and the angle is, if you see from here, then the angle will be 180 degree. Okay, this is basically anti-periplanar. Why the anti-periplanarity is required? Because OH minus will attack from here, so this will attack, this will attack. So this is a very smooth process. That's why anti-periplanarity is required for E2 reaction, but syn periplanarity required for this kind of reaction. Let's see how and why. So suppose I have like this. Mm, I have a group X and I have a group Y. Okay. Hydrogen, 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 hydrogen. What will happen? My Y will attack X and this bond will shift and this will shift. So basically, this will be our product. Hydrogen, 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 and X, Y. So this will be our product. So this is called, that's why this is called syn periplanar is required, because on the same side, right? So this reaction is also called syn reaction. Okay. If no external base is given, no external base is given, then what will happen? For example, I have substrate like this, OC double bond O CH3 hydrogen. What will happen? This is also kind of system where syn elimination or syn reaction occurs. What will happen here? That O will attack here, this will shift here, and this will shift here. Finally, our product is C double bond C from here and O double bond CH3 OH. So this will be our acetic acid will be product, and ultimately this ethylene will be formed. So this is basically syn elimination, or it is also called pyrolytic syn elimination. Pyrolytic syn elimination, because in this reaction heat is required. Where the heavy heat is required, we call that a pyrolytic reaction. This is basically pyrolytic syn elimination. And if there is two, two different cases are possible. If suppose if there was another hydrogen, then there will be competition between the two, isn't it? So this hydrogen is more acidic. More substituted hydrogen is less acidic. Okay. So with this hydrogen, the reaction will not occur. Okay. Because this hydrogen is more acidic as less substituted. And it is more substituted, so less acidic. So reaction will not occur from this side. Okay. From this side means it would also been like this, isn't it? So this will not occur. Okay. So I think these things are cleared. All the confusions are cleared. If you have any other queries, then let me know in the comment section. And tab tak ke liye, thank you so much.